Hello Year 10, we're about halfway through P6 here, and just to remind you, you should be adding all your notes on to your P6 knowledge organiser as we go, so about halfway through, and I will be taking you through types of radioactive decay. So if we were having this, if you're in the classroom, I'd be putting this up on the board and asking you, just like I did a couple lessons ago, what does this symbol mean? And by now, hopefully, you can recall that it's ionizing radiation. So it's a warning sign. It's telling us there's something dangerous, i.e. something that is ionizing, as opposed to non-ionizing like microwave and radio wave and infrared. Ionizing radiations, typically you'll find these in X-ray departments or anywhere that's dealing with radioactive materials that might be releasing gamma waves. So we'll go through all the parts that come out of ionizing radiation today. Does it apply to all our radioactive decay? It has to be over a certain level. We don't put these on bananas, but bananas are radioactive. And again, if we haven't had that discussion in class, don't panic, there's lots of other foods that are radioactive. Don't stop eating bananas just because I've said they're radioactive. But if you get enough bananas in a room, you can get the Geiger Müller tube to start beeping a little bit more. Okay, so the purpose of today's lesson is to define what a radioactive substance is. So we'll go through that in a little bit more detail in a second. I'll do it on this slide because it's nice and easy. Our second point will be in looking at types of radiation emitted, what's being emitted from radioactive substances, what's making them radioactive effectively. And we're going to have a look at comparing radioactive decay from different sources. Not all things decay the same way. Some things are stronger, some things only decay certain types of substances, some only do another type. So back to a radioactive substance. Okay, so you've been hearing this word decay a lot. And anything radioactive is when the nucleus, and I've started too far over there, anything that comes out of the nucleus is radioactive. So it could be a particle comes out, it could also be a wave of energy, which we've already learned about in the electromagnetic spectrum when we looked at gamma waves. Oh, a little symbol. Okay, so anything that emits either particles or energy from the nucleus is considered radioactive because what comes out can be quite dangerous. Right, the first one we're going to look at is the alpha particle. Okay, so this nucleus over here could be anything radioactive. We'll keep it nice and simple. Let's say it's a bit of uranium. Okay, it doesn't really matter what it is. Typically, we'll talk about some of the details, but this is the alpha particle here. Okay, and there's going to be three types of particles and rays that we're going to talk about. So this is the first one. And an alpha particle is literally made up of 2 protons and 2 neutrons, which, if you know your chemistry, is a helium atom. Oh, that's a helium roll. But it's missing something to be a helium atom. A helium atom would also have a couple of electrons attached. But we don't have those, because this is coming out of the nucleus. There's no electrons in the nucleus. So we'd actually write this as He2+, because it's got a positive 2 charge. In fact, it's so positively charged, it's incredibly dangerous, because it'll strip electrons off anything else it comes in contact with. Now in the classroom I'll be doing a demo shortly, which I'll film and I'll try and attach on show my homework, but you'll see how dangerous alpha particles are. Now they can obviously be shown as this here, alpha particle, He2+. You can also just be given this symbol here, okay, and it means exactly the same thing. Now if we wrote this on a periodic table, it would look like this, 4 and 2. So 2 protons and 2 neutrons gives us a total nucleus of 4. So that's the alpha particle. Now some of the key parts. We've already covered 2 protons, 2 neutrons, there's no electrons. Requires a large original nucleus. So back over this side here. We can't do this with a small nucleus. Okay, we need to have a nucleus that's nice and big and unstable. So it has to have enough in there that losing 4 parts of it isn't going to make a huge difference. And it has to overcome the forces that hold all of this together to get out here. It has to break a considerable amount of force, and that explains some of the energy behind creating the alpha particle and also the damage it can do. Now, because it's quite big, and I know we're talking about 2 protons and 2 neutrons, and you could say that's quite small, in the world of atomic particles, this is really big. This is about one of the biggest things there is. And because it's so big, it won't go through skin or paper. These are the 2 typical things we use to demonstrate this. So a piece of paper will stop an alpha particle, and your body will stop, your skin will stop. Where it becomes really, really dangerous is if you ingest it. So there was an attack in London about, 14, 15 years ago, where somebody had polonium-210 added to their tea. Now, polonium-210 is a big alpha particle emitter, and because it was swallowed, ingested, it caused a huge amount of damage and unfortunately killed the man. It was done intentionally. It actually ended up killing him. So it can be extremely dangerous. So when you see things like Chernobyl and people wearing gas masks and wearing paper suits, this is what they're protecting themselves. They're protecting them from the very dangerous alpha particle. It doesn't penetrate very far, but if you were to swallow it, breathe it in, ingest it effectively, it's very dangerous to me. Right, so the next one we're going to go to, this is a lot smaller. Okay, so here is our nucleus again. Now, a nucleus doesn't have to be quite so big for this one, but typically it's the bigger ones. And this is our beta particle. And the beta particle is very simply an electron. That's all it is. An electron, but it is moving fast. Okay, so it's a high-speed electron. Okay, so we're going to deal with the one you're used to at this stage, our B minus, which just means a beta particle with a negative charge, which electrons have a negative charge, so it's just as you know electrons to this stage. However, we do also have a B plus. Now, a B plus is when we can actually have a positively charged electron. Now, the reason why we have negative charged and positive charged electrons is because of this bit down here. And this is what's actually happening. A neutron, so a neutron down here that came out of the nucleus, was actually still inside the nucleus, it never leaves, can become a proton. Now, that's all done at the quark level, which is something we cover a lot in A level. We talk about what neutrons and protons are actually made up of. And all we're changing is the balance of how the ingredients, if you like, of what makes up a neutron. If we change the ingredients just slightly, so a neutron has 2 downs and 1 up quark, and a proton has 2 ups and 1 down, so there's not a huge difference between them. And if we change it just slightly, it becomes a proton. Now, a proton is slightly different to a neutron in the sense it has charge. Now, if this is a positive charge, then we need to release something that has a negative charge so that these 2 balance, because everything likes balance in the universe, and it means we're now back to what our charge our neutron have, which is no charge. Now, our little thing down here, an antineutrino, you don't need to know for GCSE, but it does make up the remainder of the mass, because a proton is slightly less mass than a neutron, so we need to balance that as well. Okay. Now, again, a lot of that's at A level, but you should know that a B minus is a neutron turning into a proton. Now I'll press the button. Okay, so again, this is when we have atoms with a nucleus that have too many neutrons, and the weak force at the quark level, again, that is A level, but just more information about why this is happening. Now, beta particles, the really important thing about what makes a beta particle dangerous is how fast it's moving. Because we have electrons around us all the time. We're made up of billions of electrons. But they're not moving very fast at all. In fact, the electrons moving in the electricity cables around us right now, probably moving at 3 or 4 millimeters a second, quite slowly. But these are moving closer to the speed of light. Now, beta particles will slow down when they pass through things because they do have mass and they do interact with other particles. And the more they go through things, the more they slow down. So we call it de-accelerated by electromagnetic interactions. Okay, so part of this is when we go through things like a metal sheet, or plasterboard wall, anything like that, it starts to slow down. But if we're going to deaccelerate through electromagnetic interactions, we sometimes get releases of gamma radiation, which we learned about in P5. Okay, so this is our, in a nutshell, everything we need to know. So this is our B minus, so this is a neutron into a proton, and this is our positron, coolest name in physics, which is a beta plus, which is actually a proton turning into a neutron. And you get this when you've got either excess neutrons or excess protons, and vice versa. One turns into a proton, one turns into a neutron. Excess material release as a fast electron, excess material release as a fast positively charged electron. It's still an electron. It just has a positive charge because our proton right at the top had a positive charge and it became a neutron. But we can't just ignore the charge. It can't just disappear into thin air. The charge had to come out somewhere, and it's attached to the electron. The electron becomes positively charged. And we also, and I don't have it included here, we've got an anti-neutrino on this side and a neutrino on this side. I don't draw that quite right, but effectively that's the balancing act that goes on. Okay, so the third one, so we've had alpha and beta. If you like, beta is 1. So this is the third out of third, and this is our gamma ray. Now, here is the big difference between the first two and the gamma ray. The first two are particles. They're actually physical particles. We can put them on a set of scales. We can measure them. There is no mass to a gamma ray. It is a part of the electromagnetic spectrum, and it's released, and I have put, here we go, high energy, released energy, energy in the form of a wave, and it's used to balance the atom, the nucleus of the atom, which has become unstable. It might have released alpha or beta, and it's still got some leftover energy, so it expels it as a wave, and it'll have a certain frequency. It's a very, very high frequency, which is what makes it dangerous. Okay, so gamma radiation, it's part of the ionizing part of the electromagnetic spectrum, so it means it's able to ionize other atoms. So it transfers energy into free those electrons and can bounce them off and ionize other particles. Now, it usually occurs after alpha or beta decay. It cannot occur on its own. You can't suddenly have spare energy in a nucleus that's nice and happy. It won't release it. Okay, that it has to be an unbalanced nucleus, and it's releasing energy. So it usually occurs after alpha or beta. So the source that we keep in the school is actually an alpha and beta emitter. So it has alpha particles and beta particles emitted. And also, obviously, it releases gamma radiation because of those two to balance it. You sometimes get some radioactive materials. Cobalt-60 is a good example, which is an alpha emitter. Doesn't release very many beta, just a few, but again. Okay guys, this is the point in the lesson where I would be doing the demonstration. So I'll bring in a piece of radioactive material, it's a piece of radium. It is ionizing radiation. There will be a safety notice read out in class. I will try and record the demo I do with the Geiger meter tube and a piece of radium, and I can post that separately so you can watch that at this point. So it'd be a good point to dive out of this lesson, watch that video and come back in. Okay, so why don't we all die from exposure? What stops us from being constantly bombarded by alpha, beta and gamma? So the simple answer is we're not. We're always bombarded by all three. But these are the parts that we typically apply to alpha. So you might have recall that we talked about this back at alpha. It can be deflected or reflected by a sheet of paper or skin. Okay, so whilst it's incredibly dangerous, very ionizing, so this is where it's important, ionizing for penetration. Okay, now beta particle, okay, can be, now I like to put the word absorbed or slowed down, is a colloquial term, but absorbed is the scientific word we'd like to use or see using, by sheets of aluminium. Aluminium is quite specific. Other metals will have the same effect, it'll just take more of them. So it's still ionizing, so we'll just put it as ionizing, not very ionizing, but medium penetration. So it won't go through everything, and a sheet of aluminium will slow it down to the point where the electrons become so slow that they'll just join another atom somewhere that's positively charged, and I'm just looking for some balance. Now the last one, okay, our gamma, it's the least. Now I'm not going to say low ionizing, because that would be a bit of a falsehood. Least ionizing, because whilst it's still incredibly dangerous, it's nowhere near as ionizing as our alpha particles at the top. But this one has the most penetration. This one will go through everything. In fact, it takes, we typically say an inch, which is obviously imperial, so 25 millimeters of lead or 1 meter of concrete to stop most. And now I'm going to be careful here, so I'm going to say stop most of our gamma rays, because it won't stop all. It becomes a question of how thick it is, just stops more, and you just keep making it thicker and thicker until most of it stopped. So you can't really discount that some will always get through no matter how thick the walls. Okay guys, so in class we would be doing these 8 questions as a bit of a quick quiz, just to see whether we're taking in the information, we understand what we're doing, and whether you can prove to me that you're ready to move on to the next stage. So what I'm going to do, if you're watching this at home, I'm just going to reveal the first 8 questions. So 1, 2, 3, 4, 5, 6, 7, 8. What I'd like you to do is pause the video, be honest with yourselves, write down the answers, and then I'll stop talking in 5 seconds, and you can then check if you get the right answer. So pause the video. Okay, hopefully you've paused it, had a go at it, and here are the answers. Put them up. If there's anything you're not sure about, or you'd like some more information, please email me to ask. More than happy to help you out. Okay, so we're moving on to the big 6 marker. This is an old question, came out quite a few years ago, but it showed there was a big gap between what had happened in the classroom and students' ability to answer a question. Now, it's obviously a 6-mark question, which means, as always in physics, we are looking for 3 parts to our answer. So I'm going to give you a little bit of steerage here, because I appreciate there's going to be people of all sorts of ability, and hopefully you've seen the demo that I've put online for you as well, so please don't try and answer this without seeing the demo, it will make less sense to you. But in your previous lesson you should have been looking at background radiation. Now what's very, very important when you are counting radiation is that you keep taking background radiation into account. So if we have our radioactive source and we count 480, well, there would have been 11 anyway according to this when we did our background check. So it's actually going to be 480 minus 11. 325 minus 11, assuming these are all counts for 1 minute. I don't think it actually says. Let's assume it is. So 325 minus 11 and 25 minus 11. Now, that would be definitely one of the things I would expect to see in your 6 marker. But when we're looking at a 6 marker about radiation, well, we've got 3 types of radiation, and we can talk about in our 3 paragraphs. So 1, 2, and 3. We can talk about paragraph 1. We can look at the control. background radiation and alpha. That's a big paragraph, but it gets us lots and lots of marks. It shows the markers that we appreciate why there was an experiment done with 480, that's called our control. While we had a background radiation check of 11, and that we would take that away from each of them, what we just talked about, and just stating that in that paragraph would have got you loads of marks. And then of course we get to alpha. Now, if you've watched the demo, you would have seen a piece of paper stops out alpha particles, and what we'd be really looking for is the difference between 480 minus 325. That would tell us how many of those counts would have been alpha particles. Now, I'm not going to put the minus 11s in for each one of these. You can do that yourself, because I just want to use the big numbers so we can go through the key points here. Now, if you've talked about all the important stuff in alpha, the next one's nice and easy. It's going to be about beta. Now, I would love you to pause the video right now and see what you can tell me about beta. And then I'll fill in the blanks. Okay, so if you're doing this properly, and you've had to think about what beta, and you've probably written down a couple of little notes about what the difference with beta, what you'll probably notice is there's no difference between the paper being there and aluminium being there, which tells us actually there's no beta there at all. Okay, there is no beta. It's all been so far alpha or gamma. So no beta, and that was obviously a key mark for this question. And we know that because the aluminium sheet, you just have to make a statement, there's no beta, aluminium sheet added, made, no difference. Because if there was beta, putting in an aluminium sheet, we would expect to see this number here drop substantially. It didn't, so there must not be any beta involved. Now, of course, paragraph 3, nice and easy, we've got alpha, beta, and now gamma. Now, again, we might make a fairly bold statement here that out of our 480 minus 325 minus, well, that's, what was our 480 minus 325 equals our alpha. So that's 155 counts, which means of the remaining, of the 480, the remainder are gamma. So there's there's more gamma than alpha. Okay, more counts. And something that we'd be looking for, the lead, or PB, symbol for lead, didn't stop everything. Because there is still, even though we've removed our background radiation, there is still a count of 14 that got through the lead. Okay, so that's that point we're making earlier. Lead in concrete, great for stopping it, but doesn't stop everything, it just reduces what's going through. So that's a great example of a 6-mark question, and every time you get a 6-mark question, you should be thinking, what 3 parts could I write about? And when doing radiation, that's almost always going to be alpha, beta, and gamma. But please don't forget about our control and something about background radiation. That will get you all the marks. Okay, so when does decay occur? Here's the great news, completely random. We cannot predict. A block of uranium could sit there for a month and do absolutely nothing, and then in 10 minutes decay massively. It's completely random. It tends to be predictable over periods of time, so we find an average, and that tends to be reproducible. Now, we do have for every type of material a half-life, which we'll be doing a lesson on, where we talk about the count will reduce to half of what it currently is after a period of time. So things that have really high radioactivity, things that decay quickly, we would expect to see a short half-life. So for example, cobalt-60 has a half-life of 7 years. So if our count was, when we first got it, 1,000 per minute, in 7 years time we'd expect 500 per minute. It's really as simple as that, half. But this 7 years is for every different type of material. So uranium, which is a slightly tricky one for us, uranium-235, so that's the fissionable material, the things we use in weapons or power stations, certainly has a half-life of 25,000 years. So it stays radioactive for a really, really long time. Other things you'll be learning about half-life, carbon-14, which is for carbon dating, if you heard the expression carbon dating, where we're looking at being able to age materials, not to carbon atoms going out with each other. Okay guys, so that pretty much wraps up this lesson. We've defined what a radioactive substance is, anything coming out of the nucleus. We've looked at the 3 types of radiation emitted from radioactive substances. 2 are particles and 1 is part of the electromagnetic spectrum. So we've got alpha, beta and gamma as a wave. And we had a look at that 6-mark question where we compared radioactive decay from different sources. Now if you really want to push yourself and try some questions that are harder, there are some on SharePoint that you can access. In particular, look for 6-mark questions where you can put your knowledge against, can you split the question into 3 parts, and do you truly understand how alpha, beta and gamma work. Thank you very much for tuning in. Take care.